welcome to the multiple part series where we are looking at the 2017 chemistry paper, NSC or DBE chemistry paper for 2017. And so far, we've done everything from question one up till where we are now, where we are on question seven. And question seven is an acids and bases question. And this or this and the next couple of questions. Hopefully, we get to finish the entirety of the paper today. But basically, this question and the next two after this tend to be some of the most confusing questions for students. A lot of the times, students will complain about the fact that acids and bases as a topic has so much going on that sometimes it is difficult to know exactly what they are asking from you, especially once you get to the calculation and stoichiometry type questions. So we will go through this, and in going through it, I will take my time in giving much more than just the answer, but the explanation as to why, maybe, and hopefully that helps with understanding exactly how it is that you are expected to go about answering these questions. So, um, acids and bases will always start with some theory, followed by some type of a calculation question. And in this case, they say that ammonia ionizes in water to form a basic solution according to this balanced equation. And once again, they've kept through with the trend of balancing the equation for you. But had they not, you would have had to balance this yourself. Okay, so first questions first. Is ammonia a weak or strong base? Well, this is just one of those questions that you normally prepare your answers beforehand. There is a table that we normally use that tells you what the strong acids are, what the strong bases are, the weak acids are, and what the weak bases are. And ammonia is most definitely a weak base. The reason is always the same. It is a weak base because it dissociates only partially in water. And had this been an acid, we would have said ionizes partially in water. Now, what do we mean by ionize and dissociate? Well, dissociate would be as you would expect from the English meaning of the word. To dissociate, per English definition, is to maybe break up or to separate, and that's exactly what a weak base will do. Is it will separate water into OH as well as an extra H, which it intercepts to become an ion, right? Which is different from ionize, which is done by an acid. Now, again, to dissociate is the hallmark of a base because it breaks up water in order to introduce hydroxide into the fray, whereas a acid will give off of its ion to ionize water, right? Ionize itself and ionize water to form H3O plus. Okay, so ionize gives off, which is the acid, and dissociates, breaks apart the water um, in order to form its conjugate acid. Okay, and if you look at 7.1.2, there we are, asking about a conjugate acid to ammonia. That would be ammonium or NH4 plus. What do we mean? Well, in this case, the conjugate acid is what would be the acid if the reverse reaction were to occur. And in this case, NH4 plus, if you consider the reverse reaction, gives off of an H to OH to form water, and that is the hallmark of an acid. The hallmark of an acid is that it donates a proton, which is another way of referring to the hydrogen ion, and so forms ammonia from ammonium. Now, two things to note here. I'll just um, do something quickly. Ammonia versus ammonium. Now, how I always remembered it is ammonia will have an A at the end as ammonium will have an M at the end. Now, very important to note that an M is created through 1, 2, 3, 4 lines, yeah, correlating to the 4 over here, as ammonia is formed by 3 lines. That A is formed by 3 lines, which correlates to the 3 over there. If you need a way to remember it, there you go. NH3, 3 lines for the A, so NH3, and ammonium, 4 lines for the M, 4, so 4 to the H. Okay, that's just a nugget for you to help you remember. Then another thing to 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 maybe note over here is why do we call um, this thing? Why do we call this thing a proton? Yeah. So if you consider the atom itself, okay, hydrogen atom, hydrogen in its nature, as you see it in the periodic table, looks something like this. We'll have H1 and its atomic mass would be 1 as well. And what that means is the proton number is 1, so the number of protons / electrons are 1 for the neutral atom. And because this is 1, and this is the addition of the proton plus the neutron inside the nucleus, it being 1 means there are 0 neutrons present. So the atom would look something like this. Okay, 1 electron over there and 1 proton in the middle. Now, when you form an ion from hydrogen, you essentially are taking away that electron, and look what you end up with. You end up with just a proton. So essentially, that's why we call hydrogen ion a proton, because it really is just a proton left, right? Just again, a nugget for you to understand where we're coming from here. Okay, like I said, I'll take some time and I will explain exactly where we get all this information from so that you better understand what we're doing here. Then, 7.1.3, identify one substance in this reaction that can behave as an amphiolite. This word amphiolite is a word that means basically that it's a substance that can act as either a base or an acid depending on the specific need in the reaction. So sometimes it'll act as a base, sometimes it'll act as an acid. And in this case, believe it or not, both of these amphilites in some reactions. So in some reactions, you'll have water. Some reactions you'll have water act as an amphilite. Some reactions you'll have ammonia act as an amphilite. Yeah. So both of them are amphilytic, meaning they can act as either a base or an acid. Cool. 7.2. They say a learner adds distilled water to a soil sample and then filters the mixture. The pH value of the filtered liquid is then measured, right? Again, he then gradually adds ammonia. Notice there's an A, so NH3, to this liquid and measures the pH of the solution at regular intervals. Okay, every now and then you're going to add ammonia, NH3, because the A has 3 lines to it, and they will measure the pH at regular intervals. The graph below shows the results obtained. Okay, so given the fact that we are looking at a substance of pH 4 becoming pH 10, the question is the soil sample acidic or basic? Soil sample is acidic. Why? Because in the beginning, you have it have a pH level below 7. 7 would be the midpoint or the neutral point, but because it is lower than 7 in the beginning, then the soil sample is acidic. Okay, then calculate the concentration of the hydroxide ions in the mixture after the addition of 4 centimeters cubed of ammonia. Now, important thing to note here is they want us to calculate the concentration of the hydroxide ions. Now, according to the formula in your formula sheet, the pH refers to or is related to the concentration of hydronium. Or if I quickly type out what I'm speaking of, okay, the formula you're used to seeing is this. Unfortunately, we're not looking for the hydronium concentration, but rather the hydroxide concentration. But you do have another formula that you can use to answer this, and that formula is also on your periodic table, and that formula is specifically this. Remember this formula? That's what we're going to make use of. Okay, so to start things off, after 4 centimeters cubed of NH3 is added, we're looking at that. And basically, oh my word, try that again. Basically, we are looking at a pH of 6. Okay, each gradient in this case is a value of 2 from the previous gradient. So therefore, this point, you're looking at 6. Okay, so pH of 6, okay, substituting in now, 6 equals negative log, and we don't know what our hydronium concentration is, so we'll say H3O plus, and we'll use that to find it. So using this, our H3O plus concentration is therefore, if you plug it into a calculator, equal to, you know what, let me do it this way. Okay, is equal to times 10 to the negative 6 moles per decimeter cubed. The answer. But that is the answer for the concentration of hydronium. We now need to plug this value into that formula in order to find the rest of our answer. So if I just move that to the side, what we now have is, well, that 1 10 to the negative 6 that we had is the concentration of 1. The concentration of OH minus the other thing that we're looking for, and this is all equal to 10 to the power negative 14. Okay, so let's just add that over there. Okay, and if you take this to the other side, you end up with the fact that the concentration of hydroxide is equal to 1 times 10 to the power of negative 8. Okay, or if I write this a bit nicely, right there. Yeah, moles per decimeter cubed, goes without saying. Okay, now would be 7.2.2. So understanding the fact that even though they want the concentration of hydroxide, but you can only find the concentration of hydronium, there is an equation that relates both of them over here, and you would still be able to find the answer. The other parts would be to notice that the volume is 4 when the pH is 6. Okay, pretty straightforward. Let's move on. We look at page 12. 7.3 is a titration question. Nope. I take that back. That is not a titration, but rather a reaction a multi-stage reaction that is used to find the concentration of an HC sample. Not necessarily a standard titration as you used to, but let's work with it regardless. Okay, given the balanced equation for this reaction, and you're asked to find the concentration of the hydrochloric sample. Now, there's a lot to this question. There are two stages to this question as well. That over there being stage number 1, and this over here being stage number 2. Now, a lot of people fail to identify that given that there are two stages, there will be two stages to your calculation as well. Okay, just note that there are two stages to the reaction, so there are two stages to your calculations. Okay, let's actually read through this and let's identify everything we need. I will highlight the volumes in one color. I'll highlight the concentrations in a different color and number of moles if we're given in a different color as well. So, or better yet, let me do this. I'll highlight everything related to HCl in one color, everything related to water in a different color, and everything related to sodium carbonate in a different color as well. Okay, so 5 centimeters cubed of the hydrochloric sample. Also told that 50 centimeters cubed of this dilute hydrochloric acid solution is reacted. Oh, so this is for the second stage now over here that is reacted. Reacts completely with that much of sodium carbonate. Okay, let me actually go against highlighting because it seems to illustrate the entirety of the reaction very, very well over here. So we can keep it over there. Let me jump straight into working things out here. First things first, what you want to do is to work backwards, in actual fact. You want to work backwards given the fact that over here you have the balanced equation. Right? You're given the balanced equation for this reaction over here, and you want to calculate the concentration of this sample over there. So we're going to start over here and work our way backwards. Right? So first things first, let us find the number of moles for the Na2CO3, because once we find that, we can at least translate it to this. Okay, noting, by the way, the mole ratio of 1:2. Okay, no problem. Let's tackle this. And the number of moles of Na2 CO3 will be given as follows. Is equal to the mass over the molar mass, and if you allow me to skip that formula in favor of writing the substituted in values, we have 0.29, which is given to us. The molecular mass of the entirety of that, 23 times 2 plus 16 times 3 plus the molar mass of carbon gives you 106. Okay, that would have given you a mark. You put that over here. Then after that, you find it to be equal to, once you plug it into a calculator. Let me do that quickly. 2,74 times 10 to the negative 3 moles. Yeah, place that over there. You move it. No, it's fine. That is the number of moles. Then, in order to translate the number of moles over here to get it to hydrochloric acid number of moles, what you do is, and this is how I remember it, you divide by where you are, you multiply by where you're going. So in this case, we divide by 1, which is the mole coefficient for sodium carbonate, and we multiply by where we're going, which would be 2 with hydrochloric acid. So essentially, we're going to take this and multiply by 2. Right? 2,74 times 10 to the negative 3. And that is multiplied by 2 to give you 5,47 times 10 to the negative 3 still. Right? Here we are. Okay. That is the number of moles of hydrochloric acid. The dilute version of the hydrochloric acid. Okay. So now we need to take it back a further step. So therefore, to find the concentration of this dilute version, we're going to say okay, again, we're still working with the dilute version. We're going to say, well, the number of moles over the volume, N over V, is equal to 5,47, which we just found, times 10 to the negative 3. Just write that like this. Times 10 to the negative 3, right, over the volume that was given to us as 0,05, given to you in the question itself, right? Right there, right? The 50 centimeters cubed, which I converted into decimeters cubed by multiplying by 1,000, and you end up with 0,05. And that's what we use to substitute into here. Our answer is therefore equal. Answer is therefore equal to 0,1094. And that is in moles per decimeter cubed. Right over there. Right. At this point, we've made our way to this, where we have just diluted the water, but now we want to take it a step back to the HCl sample. So what we then do is we say, well, the concentration and volume of the non-diluted, the number of moles of the non-dilute sample should be the exact same as the number of moles of the dilute sample, because all that changes is the fact that you add water to it. You didn't add or take away the amount of hydrochloric acid, but you just changed concentration and the volume, right? So because of that, I'm now going to say concentration of the sample as well as the volume of the sample should be the exact same as the concentration of it being dilute as well as the volume of it being dilute. Okay, place that over here. And the concentration is what we're looking for. Concentration of it in its sample form is what we're looking for. We know the volume of the we know the volume of it being non-diluted. We know that to be 5 centimeters cubed. Okay, and that entire thing is equal to the concentration of it being dilute, which is 0.1094 that we just found, multiplied by 500. And the reason why we're able to neglect the units here, or not to convert the units, is because they're all, in this case, both of these volume units we are going to keep in centimeters cubed form, and they cancel each other out. So no need to convert it. If you converted it though, that's also fine, but you could have left it as is. Okay, multiply this, take the 5 to the other side by dividing, and essentially what you end up with is concentration of the sample is therefore equal to 10,94 moles per decimeter cube, which is very, very, very potent. Um, yeah, it's not something you see every day. But I guess in this case, that's exactly why they needed to dilute it, okay, with a lot of water. Because again, 495 centimeters cubed was a large dilution for the 5 mils of hydrochloric acid, right? Question 8, new section. And in this case, we are doing electrochemistry. Okay, I'm about to tackle an electrochemistry question. And to start things off, we are looking at a galvanic cell. Galvanic cell that has aluminium as one part, um, as one anode, as one electrode. We don't know if it's the anode or cathode yet, but it is an electrode, and we know that silver is the other electrode. Now, the right-hand side electrolyte that is used is silver nitrate, and well, I mean the left-hand side will be like, okay, write down the name of the component Y. Well, the component Y is in this case our voltmeter that is used to determine the voltage in this galvanic cell. Okay, is aluminium the cathode or the anode? Now, this is the question I had answered essentially at the beginning by error. It is at the anode. Okay, why? Because at the anode is where in this or the anode in this case is the negative electrode, and by doing question point 8.1.3 we will determine why exactly aluminium is the anode. 8.1.3, write down the overall net cell reaction that takes place when it is working. Okay, so what we're looking for something like this. Okay, and this is let's just leave this over here. Okay, we're gonna come back to it. We're gonna come back to it pretty soon. But essentially, the net ionic equation is as follows. Okay, that is the balanced form of the overall cell equation that takes place. And the reason why we say aluminium is the anode is because if you look at this, aluminium loses electrons to form its ionic form. Okay, and loss is oxidation, and oxidation happens at the anode in a galvanic cell. So aluminium is the anode because of that, which makes silver the cathode because it gains and is reduced. Okay, now going back to this. Remember I said we're going to use it pretty soon. And this is where we now use it. Okay, knowing that oxidation is for aluminium and reduction is for silver, all you need to do is take your table of standard electrode potentials, look each of them up, which I am about to do, and substitute in your values. Okay. Right, there you go. And right there, you would have calculated 2.46 volts, okay, which is the initial EMF of the cell. Does it remain that throughout its usage? No, obviously the voltage would go down as the cell is used. So therefore, that's why we need to specify that it's the initial EMF. Okay, let's see. Then consider the half cells P, Q, and R represented in the table below. We still are looking at galvanic cells, and so that's why it's still question 8. And it's 8.2. Write down the name of the suitable electrode for half cell Q. Oh, different combinations of the half cells are compared to determine the highest EMF produced. Understand conditions. Seen that, but again, write down the name of the suitable electrode for half cell Q. Well, in this case, you'd have two options. The two inert um, electrodes options are platinum and carbon. Why platinum and carbon? Because chlorine gas exists as a chlorine gas exists, well, as a gas, and so therefore, because of that, can't really exist as a electrode in itself. Otherwise, the gas will all escape, and so needs to be used in conjunction with an inert electrode in order to facilitate the reaction. Okay. Now, state the standard conditions under which the half cells should operate to ensure a fair comparison. Okay, this is now just theory work that you would have studied before the paper. Standard concentration of 1 molar, 1 molar representing moles per decimeter cubed. A standard temperature of 25 degrees Celsius and the standard pressure of 101,3 kilopascals. Let's just move that to the side. There you are. STP, standard temperature and pressure, as well as standard concentration as well. Write down the name or formula of the strongest reducing agent in the half cells above. Well, look at table 4b, and you should be able to tell that zinc is the strongest reducing agent in this case. So zinc would be your answer. And depending on what you write down, either write zinc like that or zinc like this. Okay, which combination of half cells would produce the highest EMF without calculating anything? PR, PQ, or QR. Now, the secret to this is you want the two that are furthest away from each other on the table. Again, I'll repeat, the two that are furthest away from each other on the table, and that would be P and Q. Zinc and chlorine are furthest away from each other on the table, as opposed to zinc and copper or chlorine and copper. Okay, and that would be 8.2.4. And that is it for question 8. Let's see how we're doing for time. Not too bad. I think we'll end it here for this question. In the next one, we will tackle question 9 as well as question 10. Cheers.